Hello, my name is Camille Stagg. I'm a research ecologist with the US Geological Survey at the Wetland and Aquatic Research Center in Lafayette, Louisiana. And today I'm happy to share with you our use of SyncroSim in development of a model called LUCAS, the Land Use Carbon Simulator, and how we've applied it to wetland restoration scenarios across the country, and how that information can be used by land managers and policymakers who are focusing on wetland restoration as a nature-based climate solution. First, I'd like to acknowledge all of my collaborators and funding partners. This is a very large team. We've been working together for many years to develop this framework for assessing wetland change impacts on carbon sequestration. And we have partners from across the US, including federal, state, local partners, as well as our colleague and collaborators from Apex, who have been working with us on this throughout the project. So coastal wetlands are important to climate policy and planning simply because they can sequester large amounts of carbon. In healthy wetlands, regular tidal flooding leads to soil carbon accumulation deep in the soil, and this carbon is effectively sequestered and stored there because of very low rates of decomposition in these flooded environments. And so carbon sequestration can help to mitigate climate impacts by reducing greenhouse gas emissions. This has a feedback on coastal resilience. So as temperatures decrease, climate threats to coastal wetlands also decrease. And so there's a positive feedback here in coastal wetlands. And many agencies and managers are taking advantage of this synergistic ecosystem service in coastal wetlands, trying to trying to take advantage of this increased carbon sequestration in wetlands. And because wetlands are playing a larger role in these climate mitigation strategies, it's really important for us to understand better and quantify the effect of changes in wetlands on carbon sequestration. How does wetland restoration affect carbon sequestration? And conversely, how can wetland loss affect carbon sequestration or even emissions? So wetland loss is a big problem in coastal wetlands because of sea level rise. Sea levels are increasing and causing coastal wetland loss through edge erosion, as well as interior drowning of wetlands due to prolonged flooding. This can also happen because of extreme storm events and other climate change threats. One large area of uncertainty is the fate of carbon following this transformation from a vegetated wetland to open water. And that's something that we are addressing in our research and our use with LUCAS and this modeling framework. How does this conversion impact carbon sequestration? So today, Eric Ward previously talked to you about the updates to the LUCAS model to include wetland-specific stocks and fluxes, and I'm going to focus on the integration of the wetland model with the terrestrial ecosystem models and how we've applied it across the country and at multiple scales, at the national scale, at the state and regional scale, and at local park levels as well. So LUCAS in general is a very powerful tool for quantifying carbon consequences of land change, and it has been applied successfully at the CONUS scale, like in this example in this paper by Ben Sleater and others, quantifying the effects of changes in forests, ecosystems to total ecosystem carbon. And so originally this model was set up to assess terrestrial ecosystems. We're working to incorporate wetlands and the carbon consequences of wetland change. The Lucas model is made up of two main submodels that are integrated within SyncroSim, and those include a landscape simulation model, or STSIM, and then the carbon budget model, which is also called a carbon stock flow model, so that changes in land cover track changes in land cover are associated with changes in carbon sequestration. The landscape model is parameterized using nationally available imagery data from NLCD as well as CCAP, and the carbon budget model is parameterized using field data that provides both information on carbon stocks and fluxes. One of the really important strengths of the Lucas framework is the ability to use future scenarios in land management, climate change, to help managers understand and quantify the impacts of restoration or land loss on carbon dynamics. So as I mentioned, our model uses NLCD for most of the land cover classes, and for wetlands, what we've done is introduce the CCAP data set for tidal wetlands, which increases the resolution or the number of wetland cover classes in tidal or coastal wetlands. CCAP has 4 different wetland classes. So we have a fresh forested class, we have a fresh herbaceous class, we also have a saline forest or mangroves, and salt marshes. So we have these 4 wetland cover classes for our coastal wetland ecosystems, and in the non-tidal or inland wetlands, we have from NLCD a woody wetland class and an herbaceous wetland class. To provide finer resolution within the forested ecosystem classes, we also use the FIA data set to provide 28 or 29, I think 28 different forest type groups across the U.S. And for wetlands, this is primarily dominated by just 1 or 2 forest types, mainly the oak gum cypress forest type. So that was the landscape part of the model. For the carbon budget model, the main carbon budget model is based on this publication by Kurtz in 2009. It's the CBM CFS3, which parameterizes carbon stocks and flux in forests using IPCC Tier 3 parameters. And so for all of the updates to the carbon budget model for all of the new wetland cover classes that I was talking about, we start with this carbon model and then adjust it by either removing or adding stocks and fluxes. For the herbaceous wetland model, this is what Eric Ward presented in much more detail in the previous talk, and I'll just briefly go over it here. The herbaceous ecosystem is more simple than the forest ecosystem, so we were able to remove a lot of these stocks and fluxes just by removing all of the woody components. So simplifying the carbon budget model significantly. And what we ended up with was this 5-stock model, but we added also some important fluxes, including the dissolved carbon flux with the blue arrows, and also this deep soil pool, which I've mentioned several times, where we can have carbon accumulation in the soil so that over time this deep soil pool increases in wetlands. And this is something that is unique to wetlands and is one of the reasons that so much carbon can be stored in these systems, is because of this burial. The wetland forest is another wetland model that we're working on updating right now. And we started with the forests from the CBM carbon model and adjusted it for wetland forests. And the biggest changes really were the inclusion of the lateral flux of dissolved carbon in the blue arrows, as well as the burial function and the deep soil pool here. So when we put all of that together, the landscape model and the carbon budget model, this is an example of the output that we get. We track the changes in land cover and carbon over time, and we can look at different scenarios of land cover change. In this figure, it's an example from some of our work with the National NRCS, Natural Resource Conservation Service, in Kentucky and Tennessee. And the red line here represents a business as usual or no restoration. The blue line represents their efforts to restore agricultural land to forest over time. And so we can see the consequences of the restoration effort in blue as agriculture in 2021. When forests are restored, we see a significant increase in carbon over time. So as I mentioned, today I wanted to highlight some of the applications of this framework that incorporates wetlands and integrates the wetland and terrestrial ecosystems in different areas across the country at the state, regional, and national level. So we've been working over the last 3 years to parameterize the Lucas model for different wetland restoration activities. With the National Park Service, we are working in 3 different parks across the country: Yosemite, Indiana Dunes, and Captain John Smith. And our goal is to develop a national model for the Park Service that assesses carbon sequestration for all wetland restoration activities across the parks. We're also working in Kentucky and Tennessee with NRCS to assess the impact of forest wetland restoration on carbon sequestration through their wetland easement program. And then at the state level, we're working with the state of Louisiana to assess coastal restoration and inland restoration of wetlands to inform their climate action plan. So how wetland restoration can help to mitigate greenhouse gases at the state level. So the first example is with the NRCS, as I mentioned, where the primary goal is to convert agricultural land or cropland to wetland forests. And we had 648 easements that we did this for across Kentucky and Tennessee. On the left end is an example at the easement level of what land change looked like over the historical period of the restoration program, from 1998 to 2021. So we saw a significant increase in the wetland forests over time during this program. The carbon consequences of this land cover change. And this figure here shows the integrated landscape across all of the 648 easements. So the overall impact of the restoration program from NRCS. We initialized the model in 1800 and then defined a clear cut around 1900, which was occurring regionally. And so following the clear cut of the natural wetland forest, there was conversion to agriculture in the area, and we can see a decline in carbon. That's in the red line is the conversion to agriculture, and continuing into the future would be the business as usual, so no restoration program. The blue line represents the restoration program by NRCS. So in 1998, implementation of restoration, so that's the conversion of cropland to forested wetland, we see significant increases in carbon. By the current current day, that's approximately 300,000 tons of carbon that has been sequestered since the beginning of the restoration program. And then we can project out into the future to get estimates of future carbon sequestration based on current land cover. So that was a regional look at some of the work that we're doing with NRCS. And the carbon assessments occur also at very local levels, at the easement level, state level, and regional level. In addition to the NRCS work, as I mentioned, we're working with the National Park Service. And for this opportunity, we are using the Lucas model in 3 different national parks to parameterize the carbon budget model for 3 different kinds of wetlands. And then our goal is to then expand to all of the national park wetlands across the country. This is an example of some of the work we're doing in Yosemite, where they are converting, the restoration activity is focusing on the conversion of bare ground erosional gullies to montane wetlands or meadows. And so we're showing here the user interface in SyncroSim. We can see on the bottom right the change in land cover from 2022 to 2050 with the proposed restoration. We see changes in carbon spatially as well as tabular on the left-hand side. So we're working to help the planners to quantify the potential impacts of their restoration activity on carbon sequestration. And again, working to do that across the country for all wetlands and national parks eventually. The third project that I wanted to highlight is at the state level for the state of Louisiana. Eric Ward talked about the Ecoregion 73, the herbaceous model, and that played a large part in this work where we've expanded into all of the state, across the state, and integrated across terrestrial ecosystems as well. So the goal of this project is to help the state of Louisiana inform its climate action plan. Currently, on the bottom right-hand corner, you can see this is their model for future greenhouse gas emissions. The wetlands are not included in this model. They are the dotted line shaded area on the bottom. And so our goal is to provide data that will inform these projections for the policymakers and the strategy document for this climate action plan. A big component of that is to use the Louisiana Coastal Master Plan, which has proposed over almost 200 different restoration projects across the state. And so we're working with the state to use projections of land cover from these projects and include that in our Lucas model to assess carbon sequestration associated with all of these coastal wetland projects. And I wanted to mention as well that land loss is still an important component of this work. Even with the Coastal Master Plan restoration, they're still expecting some land loss. And our work with Eric Ward showed the historical land loss and the carbon consequences of that land loss. And while overall we still saw an increase in carbon, so accumulation of carbon over time, the loss of the wetlands really represents that lost potential carbon, the loss of the potential carbon sequestration that could have happened with restoration. So our goal is to help these managers and policymakers understand and quantify the impacts of wetland restoration, but also the impacts of potential wetland loss in the future. Our next steps are to, as I mentioned, expand this work to the national scale. We have some national data sets that we've been working on to help us do that in coastal and non-coastal wetlands. We also want to incorporate methane, something that we are working on including in the next steps of our model. We're also working with the Department of Defense to assess carbon in wetlands at installations across the country. So that's all to come in the near future. And I appreciate your time today. Thank you.